It's a strange question. Is reality pixelated, like a computer screen? From a distance, the image on your monitor looks smooth, where you see curves, gradients, and continuous motion. But if you get a magnifying glass and look very, very closely, you see the truth. The image is made of tiny, distinct squares, red, green, and blue pixels. It's a grid. A collection of individual units that only create the illusion of a smooth reality. So, is the universe like that? Is the smooth, continuous space you move through just an illusion? If you could zoom in far enough, would you find that reality is also made of fundamental, indivisible pixels of space and time? Would you find a smallest possible length? A shortest possible moment? The answer is, we don't know. But it's one of the deepest and most important questions in all of physics, and thinking about it forces us to confront the limits of what we know about the cosmos. It takes us to a place where our two best theories about the universe completely fall apart. To understand why we even ask this question, you have to know about the big problem in modern physics. It's a conflict, a fight between two giants. On one side, you have Einstein's theory of general relativity. On the other, you have quantum mechanics. Both are incredibly successful. They are the most well-tested and accurate theories humanity has ever produced. But they don't play well together. General relativity is the theory of the very big. It describes gravity. It tells us how planets orbit stars, how galaxies form, and how the universe expands. In Einstein's world, space and time are not just an empty stage where things happen. They are a single, unified thing called spacetime, and this spacetime is dynamic. It's a smooth, continuous fabric. Massive objects like the sun warp this fabric, like a bowling ball on a trampoline. And that curvature is what we feel as gravity. The Earth isn't being pulled by the sun. It's following a straight line through curved spacetime. The key words here are smooth and continuous. According to relativity, you can always, in principle, zoom in further. You can always divide a distance in half. There is no smallest piece of the fabric. It's a perfect continuum. Then you have quantum mechanics. This is the theory of the very small. It describes the world of atoms and particles, electrons, photons, quarks, and its main rule is the exact opposite of relativity's. In the quantum world, things are not smooth and continuous. They are chunky. They are quantized. That's where the name comes from. Think about a ramp versus a staircase. General relativity's spacetime is a ramp. You can be at any height along it. Quantum mechanics describes a world of staircases. You can be on the first step or the second step, but you can't be in between the steps. Energy, for example, comes in discrete packets called quanta. An electron in an atom can't have just any old energy level. It can only occupy specific allowed energy states. To move from one state to another, it has to jump. It absorbs or emits a packet of energy, a photon. It can't slide smoothly. For most of everyday life, this conflict doesn't matter. General relativity handles the planets. Quantum mechanics handles the computer chips. They operate in different domains. But there are a few places in the universe where the two must meet. Places that are both incredibly massive and incredibly small. The two main examples are the center of a black hole and the very beginning of the universe at the Big Bang. In those places, you have a huge amount of mass and energy squeezed into a tiny, tiny volume of space. To describe that, you need a theory of gravity relativity and a theory of tiny things quantum mechanics. And when you try to put the equations together, they break. The math spits out nonsense. It gives you answers like infinity, an infinite density, an infinite curvature, an infinite anything in physics is usually a sign that your theory has stopped working. It's a red flag saying, you don't understand what's happening here. This breakdown is the holy grail of theoretical physics. It's the search for a single, unified theory that can describe both gravity and the quantum worlds. A theory of quantum gravity. And it's this search that leads directly to the idea of a pixelated reality. The place where this breakdown happens is called the Planck scale. This is a scale of measurement so small it's hard to even describe. It's named after Max Planck, one of the founders of quantum theory. Around the year 1900, he realized that you could take the fundamental constants of the universe and combine them in a way that gives you a fundamental length, a fundamental time, and a fundamental mass. These constants are the speed of light c, which is central to relativity, the gravitational constant g, which sets the strength of gravity, and Planck's constant h-bar, which sets the scale of quantum chunkiness. These aren't just random numbers. They seem to be baked into the very fabric of our universe. By mixing these three numbers together, you can cook up a length. It's called the Planck length. It is about 1.6 times 10 raised to the power of 35 meters. That number is meaningless to most people. So, Let's try to put it in perspective. The smallest thing you can see with your naked eye is about the width of a human hair. An atom is about 1,000,000 times smaller than that. A proton in the nucleus of that atom is about 100,000 times smaller than the atom. The Planck length is about 100 million times smaller than a proton. If you were to scale up an atom to be the size of the entire observable universe, the Planck length would be about the height of a single tree. It is mind-bogglingly absurdly small. There's also a Planck time. This is the time it would take light, the fastest thing in the universe, to travel 1 Planck length. It's about 10 raised to the power of 43 seconds. It's the shortest possible tick of a clock that we can even conceive of. So what's so special about this scale? It's the point where everything goes haywire. It's the scale where the force of gravity becomes just as strong as the quantum forces. At this tiny scale, quantum mechanics says that space-time itself should be a bubbling, chaotic foam of energy. Tiny virtual particles pop in and out of existence constantly, creating tiny fluctuations. General relativity says that energy and mass curve spacetime. So these tiny quantum fluctuations should be curving and twisting spacetime on this minuscule scale. The smooth, gentle fabric of Einstein's spacetime becomes a violent, turbulent mess. The very ideas of length and duration start to lose their meaning. How can you measure a distance when the very ruler you're using is fluctuating wildly? It's like trying to measure the coastline of a country with a ruler that's constantly changing its own length. This is the frontier. Our current physics cannot see beyond this wall. And it's here that the idea of pixels becomes a serious possibility. Many physicists believe that the Planck length isn't just a limit of our theories. They think it might be a fundamental limit of reality itself, a smallest possible distance, a point at which the concept of smaller ceases to exist. If that's true, then the universe is fundamentally discrete. It's a grid. The smooth ramp of space-time is an illusion. Up close, it's a staircase. The steps of that staircase are 1 Planck length high. This isn't just a wild guess. Several major approaches to creating a theory of quantum gravity lead to this exact conclusion. They arrive at it from different directions, but they all point to a grainy, pixelated cosmos. One of the most popular is called loop quantum gravity. This theory takes Einstein's idea that gravity is the geometry of space-time and applies quantum rules to it. It quantizes space-time itself. In loop quantum gravity, space is not a smooth backdrop. It's a network. It's built up from tiny, discrete loops of gravitational fields. Imagine a piece of fabric. From a distance, it looks like a continuous sheet, but up close, you see it's woven from individual threads. Loop quantum gravity says space is like that fabric. It's woven from fundamental one-dimensional loops. These loops connect to form a network called a spin network. Each line in the network carries a quantum number representing an area. Where these lines meet, they enclose a volume. According to this theory, you can't have just any area or any volume. There is a smallest possible area. There is a smallest possible volume. And these smallest possible units are on the order of the Planck scale. You can't have half a pixel of space. A region of space is built from a whole number of these fundamental atoms of volume. So space itself is quantized. It's literally made of tiny chunks. Time is also quantized. It flows in discrete ticks, not as a continuous river. The universe, in this view, evolves by the spin network changing its connections, one discrete step at a time. It's like a cosmic movie, where reality advances frame by frame, with each frame being about a Planck time long. Another major contender is string theory. String theory takes a different approach. It doesn't start by quantizing space. It starts by quantizing stuff. It says that the fundamental particles we see, electrons, photons, quarks, are not point-like dots. They are actually tiny, one-dimensional vibrating strings of energy. A violin string can vibrate at different frequencies to produce different musical notes. In the same way, a fundamental string can vibrate in different patterns. One pattern of vibration appears to us as an electron. Another pattern appears as a photon. All the particles and forces of nature are just different notes played by these fundamental strings. Now, at first glance, string theory seems to happen within a smooth, continuous spacetime. But when you look deeper, things get more complicated, because the strings themselves have a size roughly the Planck length. They can't probe distances smaller than their own size. If you try to smash two strings together to see what's inside, you just make them vibrate more, making them bigger and more massive. You can't use a string to measure something smaller than a string. This implies that the idea of a point in space, a location with zero size, might not exist in string theory. The theory smears out the concept of a point. It suggests a sort of fundamental fuzziness to spacetime at the smallest scales. It's not quite a hard pixel grid like in loop quantum gravity, but it's still a departure from the perfect smoothness of Einstein's world. Furthermore, a principle that came out of string theory called the holographic principle gives another strong hint of pixelation. This idea came from studying black holes. It was discovered that the amount of information you can store inside a black hole is not proportional to its volume, as you would expect. It's proportional to the area of its event horizon, its surface. This is very strange. It's like saying the amount of data you can store on a hard drive depends on the surface area of the casing, not the volume inside. This led to the idea that maybe all the information about a three-dimensional volume of space is actually encoded on its two-dimensional boundary, like a hologram. If information is encoded on a surface, it suggests that the information itself is discrete. You can think of it like the pixels on a computer screen. The surface can be divided into a finite number of Planck-sized areas, and each tiny area can hold one bit of information. The total amount of information is finite. If the information is finite and discrete, it suggests that the underlying reality it describes might also be finite and discrete. The universe itself might be a giant hologram with the image projected from information stored on a distant boundary. And that information is stored in pixels. A third, more direct idea is called causal set theory. This theory is perhaps the most literal interpretation of a pixelated universe. It strips everything away except for two things discrete spacetime atoms, and the principle of causality. In this view, the universe is just a collection of fundamental events, or points. These points are not in space and time. They are space and time. The only other property of this collection is a relationship between the points that we call causality. Point A is the cause of point B. Point B is in the future of point A. The universe is just this vast growing network of cause and effect relationships between discrete events. The smooth spacetime we experience is an illusion. It's an emergent property. It's like the wetness of water. A single H2O molecule is not wet, but when you have billions and billions of them together, the property of wetness emerges. In the same way, a single spacetime atom doesn't have a location or a direction. But when you have a huge number of them linked by causality, the large-scale structure that emerges looks just like the smooth continuous spacetime of Einstein's relativity. The density of these points in the network determines the curvature of spacetime. Where the points are more densely packed, spacetime is more curved, and we feel a stronger gravitational pull. So we have several different theories, all pointing in a similar direction. They all suggest that the smooth world we see is just a low-resolution view of a high-resolution, grainy reality. But is there any way to test this? Can we actually see the pixels? This is incredibly difficult. Probing the Planck length directly would require a particle accelerator the size of our entire galaxy. It's far beyond anything we could ever hope to build, but there might be other, more subtle ways to look for evidence. If spacetime is a grid, a sort of crystal-like structure, it might affect how things travel through it. This brings up a major problem for many of these theories, a conflict with one of the most sacred principles of relativity, called Lorentz invariance. Lorentz invariance is a simple but powerful idea. It says that the laws of physics are the same for everyone, no matter how fast they are moving. One of the consequences of this is that the speed of light in a vacuum is constant for all observers. It doesn't matter if you're standing still or flying in a spaceship at half the speed of light. If you measure the speed of a beam of light, you will always get the same answer. But if space is a fixed grid of pixels, that might not be true. Imagine moving through this grid, and your motion relative to the grid should have some effect. Maybe light of different colors, which have different wavelengths, would interact with the grid differently. A very high-energy gamma-ray photon has a very short wavelength, maybe short enough to feel the bumpiness of the Planck scale grid. A low-energy radio wave photon has a long wavelength and would just smooth over it. If this were true, it would mean that high-energy light should travel at a slightly different speed than low-energy light. The difference would be tiny, completely unnoticeable over short distances. But we can look at things that are very, very far away. We can look at gamma-ray bursts. These are massive explosions that happen in distant galaxies billions of light years away. They release a huge flash of light containing photons of many different energies. If higher energy photons travel at a slightly different speed, then over a journey of billions of years, they should either arrive slightly before or slightly after the lower energy photons. It's like two runners in a marathon. If one runs just a tiny fraction faster than the other, over 26 miles, a noticeable gap will open up between them. Astronomers have looked for this effect. They have measured the arrival times of photons from distant gamma ray bursts with incredible precision. And so far, they have found nothing. The high energy and low energy photons arrive at the same time. This puts very strict limits on how pixelated spacetime can be. It tells us that if there is a grid, it doesn't interact with light in the simple way we might expect. This is a big blow to the simplest models of a grainy spacetime, but it doesn't kill the idea entirely. More sophisticated theories, like loop quantum gravity, don't propose a simple, fixed grid. The spin network is a quantum object itself. It's not a fixed background. The relationships in the network are what defines spacetime, so there is no special rest frame. In such a theory, Lorentz invariance might be preserved, but in a more complex way. The problem is, the mathematics is so difficult that no one has yet been able to prove it for sure. It remains one of the biggest challenges for these theories, so where does that leave us? We are in a state of profound uncertainty. We have powerful theoretical reasons to believe that reality is pixelated at the Planck scale. The conflict between our two best theories seems to demand it. Several promising candidates for a theory of everything, like loop quantum gravity and causal set theory, are built on this very idea. The holographic principle whispers that information is finite and discrete, but we have no direct evidence. And our first attempts to find indirect evidence have come up empty. The universe, at least down to the precision we can measure, looks stubbornly perfectly smooth. Let's assume for a moment that it is pixelated. What would that really mean? It would be a revolution in our understanding of reality, on par with the discovery that matter is made of atoms. It would mean that at its core, the universe is digital, not analog. It would mean there is a fundamental limit to information density. A given volume of space can only contain a finite amount of information, a finite number of bits. You can't just keep cramming more and more detail into it. This resolves a lot of paradoxes, like the black hole information paradox, which asks what happens to the information that falls into a black hole. If the universe is digital, the information can't truly be lost, it must be conserved. It would also resolve ancient philosophical problems, like Zeno's paradoxes. Zeno of Elea argued that an arrow in flight can never reach its target. To do so, it must first travel half the distance, then it must travel half of the remaining distance. Then half of that, and so on forever. Since there is an infinite number of halves to cross, motion is impossible. This paradox only works if you assume space is infinitely divisible. If there is the smallest possible length, a Planck length, then the arrow only has to cross a finite number of these pixels to reach its target. The paradox dissolves. Ultimately, the question of whether reality is pixelated is the question of whether space and time are fundamental. For most of human history, we've thought of them as the stage, the absolute, unchanging background on which the drama of the universe unfolds. Einstein changed that, showing us they were a dynamic, active participant, but a theory of quantum gravity might take it a step further. It might show us that space-time is not fundamental at all. It might be an emergent property of something deeper. A collective behavior of a huge number of tiny, discrete quantum bits of information or relationships. The way temperature emerges from the motion of atoms. A single atom doesn't have a temperature. Temperature is a statistical property of the whole group. In the same way, a single atom of space-time might not have a location or a direction. But get enough of them together, and the properties we call space, time, and gravity emerge into existence. We are like people looking at a photograph in a newspaper. We see a face, a landscape, a continuous image. We are not aware of the tiny dots of ink that make it up. We don't have a magnifying glass powerful enough to see them. So we are forced to speculate. We have good reasons to suspect the dots are there. The nature of ink and paper suggests they must be, but our eyes can't resolve them. The search for quantum gravity is the quest to build that magnifying glass. It's an attempt to zoom in on reality, past the atoms, past the quarks, all the way down to the bedrock of existence, to see if the universe is written in a smooth, flowing script, or if it's composed of a vast, finite number of digital bits. Right now, we stand at the shore of a vast ocean of ignorance. We know our current maps are wrong, or at least incomplete. They don't cover this territory. The Planck scale is the here be dragons of modern physics. And whether that mysterious land is a smooth continuum or a world of discrete pixels is a question that we may not answer in our lifetimes. But the fact that we can even ask it, the fact that we can use logic and mathematics to peer into a realm so far removed from our experience is a remarkable thing. The universe may or may not be pixelated, but our quest to find out will continue, one tiny step at a time.